Hello and welcome to my presentation. My name is Geronimo Bezerra and I'll be presenting the short paper Deploying per Packet Telemetry in a Long-Haul Network, the AmLight use case. This is the outline of this presentation. First, I'm going to start why we're monitoring every packet, what is in-band network telemetry or INT, how is AmLight using INT, how we're moving INT to production, some of the results, and a conclusion. So why is AmLight interested in monitoring every packet? We have a very specific need. We have SLA-driven applications that need real-time monitoring. So we need to be able to monitor every microburst or event that is impacting the AmLight network functions and applications. And we start pursuing a solution that monitors every packet because of the challenge that we have today with the existing application. We have SNMP and OpenFlow counters, but pulling data is now recommended in a sub 15 seconds interval. We have sampling technology, but those only export data after a few seconds. We have a lot of packet sniffing happening at 100 gig, but is a high capex and has a high OPEX costs. And we have some streaming telemetry solutions using proprietary solutions, but they only share summaries every couple of seconds. That's the reason we're moving towards in-bandwidth telemetry. So before I start telling why, let me say what INT is. INT is a P4 application that records network telemetry information in the packet while the packet traverses a path between two endpoints in the network. In INT, or this telemetry data is exported directly from the data plane, meaning that the main host processor, it's not affected, which gives us the flexibility of monitoring every single packet at line rate and in real time. And there's multiple examples, multiple options of telemetry data that you can export. You can export timestamps, ingress port, egress port, buffer utilization, sequence number, and many others. So how does INT work? Basically, picture the nodes on the extreme sides of this topology. You have node A and you have node B. Those nodes are normal nodes, normal computers that they send a payload with a TCP/IP header to a packet. And consider, let's use the node from the left side to the right side. We have node A that sends a packet to the first switch, and this switch is called INT source switch. This is the first switch in the INT domain. This is the one that makes space for the header and also for telemetry. So the first one adds the header, adds telemetry, and every subsequent switch is just INT switch, just adds telemetry metadata. And then the packet is forwarded in the normal way, same header, same procedures. But then once it gets to the final switch, what we call the INT sync switch, this switch removes the telemetry, export the telemetry to a telemetry collector, and also forwards the packet at the same time to the destination node P. So in this way, node A and node B never see any change to their packet, and the telemetry collector receive a copy of the TCP/IP header plus the telemetry data for every packet that goes from node A to node B. So what kind of metadata is exported and how this metadata is being used? So the INT switches that we have at AmLight, they leverage the Tofino chip. So we collect per switch, switch ID, ingress port, ingress timestamp, egress queue ID, and egress queue occupancy. And every telemetry report also has a timestamp, a sequence number, and the original TCP/IP headers. So from the previous topology that we saw, this would be an example of metadata where in the bottom you have the switch 5, which is the last switch in the topology, all the metadata, then you have switch 4 in white, and then switch 3 in blue, switch white in white, switch 2, switch 1 in blue again. So this shows is a representation of the telemetry data being stacked. So now that we know what INT is and how INT operates, let's see how leveraging INT improves the network operation. The first benefit would be instantaneous egress and ingress interface utilization. Since every packet is exported to the telemetry collector has access to the metadata, the timestamp, and the packet length, then it can calculate the bandwidth utilization using multiple attributes in any interval that is defined by the operator. So at AmLight, for example, we do this every 100 milliseconds, but this could be turned down or turned up depending on the network needs and the kind of events you expect to have in your network. By monitoring every 100 milliseconds, you already have the possibility of detecting very small microbursts that could impact your network operation and also impacting your real-time applications. Uh, and this gives you the flexibility because you have the metadata and the TCP/IP header. You can monitor not just the bandwidth per interface and per queue, but you can also monitor the per interface, per queue, and per attribute. For example, you can have a bandwidth uh, utilization per interface, per queue, and per VLAN, or per MPLS label, or per destination IP address, or per TCP port. And all of this with the granularity and the accuracy of having per packet telemetry metadata. So this picture shows an interval of 13 minutes, and you can see that the peaks of the traffic, for example, most of those are persona tests or data transfers, and you can see exactly when they start, how long it takes, and when they stop. And you don't see the traffic just increasing. They just go directly to the point because now we have the accuracy. We know exactly when that data transfer started and when that data transfer stopped. Something else that we can do by leveraging metadata is monitoring the egress interface queue utilization or buffering. So now with INT per packet, and we have the information of the queue ID, meaning what was the queue that was used to send the packet out of the switch. And we know the utilization of that queue at that specific point in time, then we have this queue utilization that tells us how much buffering is being used per switch, which leads to a better evaluation of the QoS policies. And this makes it very easy for us to detect sources of packet drops. Since the packets that are dropped, those are the packets that could not make to the queue because that queue was full or that buffer was full. So this picture on the left side on the bottom shows the average buffer utilization of this switch when there's no congestion. You can see that the buffer is using 10 kilobytes, 20 kilobytes, 30, 40, 50 kilobytes. It's just a few kilobytes of buffer utilization. But then you have an under congestion moment where you see that one specific buffer was being used by almost 2 megabytes of packets that were in queue waiting to be serialized out of that switch, out of that interface. And that clearly is going to have impacts down the road, which is going to affect the hop delay or is going to affect the jitter, which is the next metadata we're going to investigate. So by leveraging the metadata that we have of ingress timestamp and egress timestamp, we can calculate jitter per packet, and then we can narrow down to which switch was the one that introduced that jitter. So this is very helpful for mitigating QoS issues or impacts to real-time applications or mitigating traffic engineering issues. And you can see here an example on the bottom on the left side, an average hop delay in microseconds, where the packets usually take from 1 to, let's say, 3 microseconds to be serialized out of that switch, or is the time that the packet takes to get inside the switch and get out of the switch. But look at the figure on the right side. So this is the same moment of the previous picture where we had a large buffer utilization. A bigger buffer means that there's a long queue, which means that the packets take longer to get out of that box, which impacts those applications. And here you can see in this figure that instead of having microsecond delay to serialize a packet, now the packets, some of those packets are facing all the way to 65 milliseconds to get out of that box, which means that the hop delay increased in thousands of tens of thousands just because there was this microburst that was using the buffer at that specific point in time. So if you have a real-time application introducing 70 milliseconds in just one hop, that has a serious impact to your end-to-end application. Something else that is very helpful when you have INT metadata is the proof of transit. So proof of transit means that you're going to trace the layer 1 and also you can trace the layer 2. So you can trace which ports were used including if that's a layer 2 domain, layer 3 domain, if you have equal cost multi-hop, or if you have spanning tree, if you have link aggregation, it doesn't matter. It's going to report exactly the port that was used, the physical port, and if you have any sort of tunnel like link aggregation or any other tunnel, then it's going to give you the virtual port. In our case, we only take the physical port. So by being able to track the physical ports in the path per packet, you know exactly what was the path taken by that packet, which is very helpful when you have a complaint that there was a problem yesterday, and I lost some packets, and you want to go back and say, what was the path that was being taken at that point in time, and then you start the troubleshooting from there. And again, it doesn't matter if you have link aggregation, if you have ECMP, or even if you have hash errors, you're going to get the physical port that was used for that packet, not that flow, that packet. So this is also very helpful to detect unstable links. So if there's a lot of flaps, for example, if you have 1,000 flaps within 1 second, there are multiple possibilities that these packets are going to be flapping back and forth. And then if you start seeing this at the telemetry collector, then you can notify your network orchestrator to make a change. And something else that the proof of transit does is that not just we know what were the ports used, the incoming port and the egress port, we also know what was the queue that was used. So these, for those who troubleshoot like QoS policies or traffic engineering policies, this is a major information because you don't need to keep looking at the counters and counting those counters and making sure that those counters have are accurate to the traffic that you're generating. For example, if you're creating a traffic engineering policy for voice over IP. So now, if you have a voice over IP traffic, that traffic is going to tell you what was the path and also what was the egress QID, which means that you can validate if the QoS policy forward that packet to the proper queue. So this is one use case that I want to demonstrate in this presentation. Is mitigating a possible malicious, possible microburst. So the idea here is to compare the kind of visibility that INT gives you when you monitor every packet with the kind of visibility that you have when you're using a sampling or a pooling approach like SNMP. So on the top, you have INT. On the bottom, you have SNMP. For the SNMP, we collect the data, the counters from the interface every 15 seconds because the switch that we use in production only update those counters every 14. So if you monitor less than 15, it's not going to give you any other data. But INT, as I mentioned before, it does that per packet. So you can see clearly the difference. When you have INT monitoring per packet, then you can clearly see that we had 5 bursts that last probably between 3 and 5 seconds, and some of those bursts reached all the way to 50 gigabits per second. If you look at the bottom, you're going to see that just by doing pulling data every 15 seconds, I don't have the same visibility. I don't know how much bandwidth was used for sure because it's only reporting 13 gigabits per second. And it gives the idea that there's just one big flow or just two flows that are spread through all this interval of multiple minutes, which does not give you the accurate vision. So if someone comes back to you, so look, I'm trying to use the bandwidth, but it looks like there's something happened that my bandwidth is being impacted. If you look at your SNMP graph, you're going to say, well, but I still have 87 gigabits per second of bandwidth available. So what was the problem? But if you look at through the INT, you're going to see, oh no, I only had at some moments 50 gigabits per second. So this is a major difference when you're doing data transfers, especially those data transfers that need to be done in real time. So how we're doing this, first, let me just give a quick context. What AmLight is this international backbone that connects Latin America and Africa to the US. And every POP in Chile, US, Brazil, we have these INT switches that export data to INT collector, and this data process is centralized in the SCN looking glass that we call. And the idea is that we're going to have all the sites with INT capable switches by Q2 of 2022. So some of the questions that we get a lot, how many high priority flows can be handled in real time by the INT telemetry collector? So the total amount of data that we can process in our network at any point in time is 10 million packets per second using all those telemetry collectors. What is the impact caused by INT in this network? Since AmLight is a long haul network, meaning that all the links have multiple milliseconds, we understood that the INT process does not create any impact because it only takes 450 nanoseconds or 0.00045 milliseconds. So this has no impact in the overall performance or the end-to-end path. And every switch adds 24 bytes of telemetry data, and the Tofino chip has an MTU of 10,000. This is not really impacting our production, but we have to track this. And we have a network orchestrator that is very flexible when selecting what flow to monitor. You can do per source, per destination, per TCP port, per protocol. So this gives us a lot of flexibility. So some conclusions: monitoring every and any packet is possible when you have INT in your network. INT has increased the network visibility beyond our expectations because there's a lot more metadata being explored than we're assuming at the beginning. When you combine INT with the legacy monitoring tools, this gives us a lot of power to track performance issues and user complaint. INT is not here to replace the other technology solutions. Now, INT is here to aggregate to the legacy environment that you have. And as part of the future work, our plan is combining this INT data with learning tools to enable AmLight, our network orchestrator, to create reliable trends towards creating a closed loop network orchestration. So we want to create an approach where the network exports data, this data is processed, this data is, and recommendations are made towards the network orchestrator that populates the switch. And this you create a closed loop orchestration that minimize the necessity of humans doing intervention to support traffic engineering. So I hope this presentation was helpful. Thank you very much for attending this session, and let us know if you have any questions. Thank you.